Let f of x equals x squared minus 4x on the interval 1, 5. Verify that the function satisfies the conditions of the mean value theorem and find the value of c guaranteed by the theorem. Well, it's continuous, it's differentiable, that's fine. So it satisfies the conditions of the mean value theorem. Okay, I could take the derivative anywhere. And I could also know that if I graph that, it's continuous. So again, that meets those theorems. Now, this is the mean value theorem. There exists a c, okay, such that if I take f prime of c, I basically am going to use our old friend f of b minus f of a over b minus a. Remember u? Oh, brings back memories. You would be my a, you would be my b. Okay, so so if I were to do this, f of b would be f of 5, which means I take 5, plug that in, so that's going to be 5 squared minus 4 times 5, which is going to be 25 minus 20, which is going to be 5. Okay, f of a is going to be f of 1, which is going to be 1 squared minus 4 times 1, which is going to be 1 minus 4, which is negative 3. And then I have b minus a. So f prime of c has to be f of b, which is 5, minus f of a, which is negative 3, all over b, which I called 5, minus a, which I called 1. So we got the double negative, meaning you add, so 5 plus 3 is 8, 8 over 4 is 2. So I need an f prime of c that equals 2. So I need an f prime of c that equals 2. Well, f prime of x is going to be 2x minus 4. So f prime of c, I don't know why I wrote it out that way. Can I make that look like an f? Yeah, f prime of c is going to equal 2c minus 4, and that has to equal 2. So I'm focusing on solving this equation right here. Add 4 to both sides, 2c equals 6. Divide by 2, c equals 3, c equals 3. All right, mean value theorem is not as rude as it sounds because of that word. Get it? Like and subscribe. Let f of x equals ln of x on the interval 1 e to the second power. Which value of c satisfies the conclusion of the mean value theorem? Well, the mean value theorem says that exists some c in the interval such that f prime of c is going to be f of b minus f of a over b minus a. Hello, old average rate of change formula. It's been a while. Unless you watch my last video, in which case it's been a minute. We'll call you A, we'll call you B. So f of B is going to be f of e squared. So ln of e squared, ln of e cancels each other out, nice little 2 drops down. Okay? F of A is going to be f of 1, which is ln of 1, which is nerfing. Okay, so f prime of c is going to be f of b, which is 2, minus f of a, which is 0, over b, which is e squared, minus a, which is 1. So I get 2 over e squared minus 1, yuck. Now I'm not done yet, because I need a c that makes this true. So f prime of c means let's find f prime of x and replace the x with c. So f prime of x is going to be the derivative of ln of x, which is 1 over x. So f prime of c is going to be 1 over c, and that so happens to equal 2 over e squared minus 1. Now, what I'm going to do is I'm focusing on this part right here. I'm going to do crisscross applesauce. So 2c equals 1 times e squared minus 1, which is just e squared minus 1. And then divide everything by 2. So c is going to equal e squared minus 1 all over 2, which is none of these options. Well, good job, ChatGPT, for giving me something that I can't even use. But that's how you do it, and that's the correct answer. So we're going to pretend that those weren't even there. I'm not going to redo the video. I'm leaving it, I'm leaving it, I'm leaving it, I'm leaving it, I'm leaving it. Thanks for watching, like, and subscribe. For which of the following reasons does the function f of x equals the absolute value of x fail to satisfy the conditions of the mean value theorem on interval -5, 5? Well, f of x equals the absolute value of x looks like this. And it just so happens that if you're -5 and you're 5, there is a nice sharp turn right there, a nice sharp corner, which means right there at 0, it is not differentiable. Which means in order for the mean value theorem to work, it has to be continuous and also differentiable, and it's not differentiable at 0. So here are our options. The function is not continuous. Oh, but it is continuous. The function is not differentiable. That's correct. The function has a vertical asymptote. That's not true. The function is not defined. That's not true. And the function fails to be differentiable at -5, which is not true because at -5 it's a straight line, so that's not true. So B is our guy. Find the critical points of the function f of x equals x cubed minus 3x squared minus 9x plus 5. Critical points exists when f prime of x equals 0. So what I have to do is I have to find out what f prime of x is and then set it equal to 0. So f prime of x is going to be power rule 3x squared, power rule minus 6x, power rule minus 9. Set that equal to 0. Factor out a 3, you get x minus 2x, x squared minus 2x minus 3. Factor that out, and you get two numbers that add up to -2 and multiply out to -3 are going to be x minus 3, x plus 1. Okay, now according to the zero product property, the two x values that will make that equal to 0 will exist at 3 and at -1. This 3 means nothing, there's no x attached. So my answer is A, 3 and -1. Fun stuff. Find the critical points of the function f of x equals 3x squared minus 2x plus 1 all over x plus 1. Well, usually when we're finding the critical points, we have some type of polynomial. Well, now we have a rational function, which means not only do we care when f prime of x equals 0, but we also care about when the original function is undefined. So we'll deal with that when we have to deal with that. It's kind of obvious. But right now we need to find where f prime of x equals 0. Now, f prime of x requires our good friend, the quotient rule. That's right, u prime v minus v prime u all over v squared. So let's find the heavy-duty stuff. U prime is going to be power rule, power rule, power rule. It's the derivative of the numerator, so 6x rather, minus 2. V prime is going to be the derivative of the denominator, so just regular 1. And then v squared is going to be x plus 1 squared. So let's put it all together. U prime v is going to be 6x minus 2. V, which is going to be x plus 1, so there's going to be foiling there. Minus v prime, which is 1, that's nice. U, which is 3x squared minus 2x plus 1. And that's going to be all over x plus 1 squared. I forgot to put the squared there. Silly me. All right. Set it equal to 0. We've got FOIL, so 6x squared plus 6x, right? Negative 2x, negative 2, distribute the -1, minus 3x squared, positive 2x, -1. And that's going to all over be x plus 1 squared. Now let's multiply both sides by x plus 1 squared. And you'll realize, wait a minute, that just makes it go away. That's kind of the point. Because we don't need a denominator where we're finding zeros. So that's nice. Now let's combine like terms up here. 6x squared combines with negative 3x squared to make regular 3x squared, like so. 6x minus 2x, plus 2x goes back to 6x. And then negative 2 and negative 1, negative 3. Let's rip out a 3. And here's going to be an issue. You can't factor that, which means we're going to have to use our old friend, the quadratic formula. X equals negative b plus or minus square root b squared minus 4ac all over 2a. A is 1, b is 2, c is negative 1. So putting all that together, you get negative 2 plus or minus the square root of b squared, which is going to be 2 squared, minus 4 times 1 times negative 1, all over 2 times 1. And so we got, that's negative 2 plus or minus 4, that'll be plus 4, so the square root of 8, all over 2. 8 is 2 times 4, so I can rip out a 2 and keep it 2 all over 2. And so when I clean this up and put it up here, all these 2's simplify to a 1, like that. And so we have negative 1 plus or minus the square root of 2. So those are 2 of my critical points. Now what we can't forget is a third critical point is going to be what makes this undefined. Negative 1 makes this undefined, so negative 1 is my other option. So kind of a very messy problem for a critical point problem, but you're going to run into messy problems, and we did it. We did it just fine. Find the critical points of the function f of x equals ln of x minus x. So what we have is critical points. Critical points exist when f prime of x equals 0. So what I have to do is take the derivative and set it equal to 0 and solve for x. So f prime of x is going to equal the derivative of ln of x, which is 1 over x, minus x. The derivative of negative x is minus 1. So let's set that equal to 0. 1 over x minus 1. Let's add 1, 1 equals 1 over x. While I'm at it, why don't I just multiply both sides by x, right? And I get x equals 1. Now you might be thinking, doesn't critical points also exist where this guy is undefined? Shouldn't we include 0? No, and here's why. Because ln of x doesn't exist at 0. You can't take the ln at 0. So our only guy is going to be 1. So kind of, you have to be a little careful with this. There's a little bit of trickery behind it, but if you kind of don't remember about the trickery and just do the problem as is, you'll be all right. Is point A global maximum, a local maximum, both, or neither? By definition, a global maximum is absolutely the very top of a graph. There's nothing greater than it. There's no y value larger than it. And A is definitely going to be a global maximum. Okay, this graph seems to be going down to negative infinity on both ends. The end behavior seems to be at negative infinity. So we could say that this is a global maximum for sure. Now, fun fact, anything that's a global maximum is also a local maximum. So it's both. Now, there's only one global maximum, and it's A. Technically, you're a local maximum right here, but I'm not asking about that thing right there. I'm asking about A, and A is considered both a global max and a local max. By the way, global is also called absolute maximum, just in case you were dying to know. Now you know. Identify the critical points of g of x. Well, critical points of a function exist when the derivative is equal to 0. Now, derivative is equal to 0 is just fancy talk for saying that the slope is horizontal. So at any points we have an instantaneous rate of change, be a flat line, we're going to have a critical point. So that happens here at B. B has an instantaneous rate of change, that is a flat line, and down here at D, you get the same exact thing. Now, critical points indicate where a graph goes from increasing to decreasing. So it would make sense that a local maximum or a local minimum would give us our critical points, and that's what B and D give us in this case. So those are my critical points right there. For the function f of x equals negative x squared plus 4x minus 3, find the intervals where the function is increasing or decreasing. All right, so what you need to do is you need to find your critical points. You do that by taking the derivative, setting it equal to 0, and solving for x. Critical points gives you a local maximum or a minimum, right? If you have the derivative, if the derivative is positive, your function is increasing. If the derivative is negative, it's decreasing. So what we need to do is find the critical points and make a sign graph based off of that information. So the derivative of f of x is going to be using the power rule. So the derivative of negative x squared is negative 2x. The derivative of 4x is plus 4. The derivative of negative 3 is nothing. Set it equal to 0, and solve for x, right? Subtract 4, negative 4 equals negative 2x, divide by negative 2, divide by negative 2, and x equals positive 2. So whatever this graph looks like, I know it changes its direction from negative to positive or positive to negative, whatever, at 2. So this is my f prime, okay? This is my derivative sign graph. What I need to do is I need to pick values and plug it into the derivative to see if I get a positive or a negative slope. So I'll pick easy numbers like 0 and 10 and plug them in and see what happens. So f prime of 0 is going to be negative 2 times 0 plus 4. 0 plus 4 is 4, which is a positive number. Now let's do the same thing with 10. Negative 2 times 10 plus 4 is going to equal negative 20 plus 4, which is negative 16, a negative number. So based off of this information, since the slope is positive all the way up until 2, we can say that my function is increasing on the interval negative infinity to positive 2. Since my derivative is negative from 2 on out, we could say that my function is decreasing on the interval 2 to positive infinity. And we kind of know that because that's a parabola that's going downward. So, if we kind of just do the whole vertex form thing, found out that x is going to equal 2 here, this all makes perfect sense. But you know what? We used calculus instead, and that's just so much better. Function f of x equals x cubed minus 3x squared plus 4. Find the intervals where the function is increasing or decreasing. All right, so what you have to do first here is find the critical points. The critical points exist where your derivative is equal to 0. So let's take the derivative and set it equal to 0. The derivative of x cubed is 3x squared. The derivative of negative 3x is negative 6x, and 4 just disappears. What I can do is factor out a 3x, and that leaves me with x minus 2. So using the zero product property, my critical points are at 0 and at 2. Hooray! Now what I'm going to do is I'm going to make a sign table for my f prime function. I have zeros at 0 and 2, and I need to type in or find out numbers that are in these intervals that I can plug into my derivative, which was this guy, and find out if I have a positive or negative number. So I'll pick negative 100, 1, and regular 100. Okay, so I'm actually going to plug into this formula because this formula will kind of help me figure out the derivative better. So I'm just going to rewrite f prime of x can be written as 3x times x minus 2, and this will actually be a little bit more convenient for me. You'll see why. Okay, so let's do all three of these numbers. F prime of negative 100 is going to equal 3 times negative 100 and negative 100 minus 2. Positive times a negative is going to equal a positive. So I don't care about my number. I just care about what I get. And so this interval right here is going to be positive. F prime of 1 is going to be 3 times 1 minus 2. Positive times a negative is going to be negative. So you're going to be negative. Let's plug in 100. F prime of 100 is going to be 3 times 100 minus 2. A positive times a positive is a positive. So it looks like I'm increasing from everything all the way up until 0. So increasing from negative infinity to 0, decreasing between 0 and 2, of course not including any of these, and also increasing at 2 and on. So 2 to infinity. And A is going to give me that. So there you have it. Given the function f of x equals sine x plus 0.5, find the intervals where the function is increasing or decreasing on the interval 0 to pi. All right, well, what I have to do is I have to take the derivative and set it equal to 0 to get myself some critical points. So the derivative of f prime of x is going to be cosine x plus nothing. So set that equal to 0. Now, if I were to inverse cosine both sides, I would take the inverse cosine of 0 and the inverse cosine of cos x, making these guys cancel out, and then I'm left with just x's. Now, cosine is 0 at 2 spots in between 0 and 2 pi. It's 0 at pi over 2 and 3 pi over 2. So I'm going to make myself a sign chart based off of that information right there. Okay, actually a cosine chart. So here's my, what did I call it? F prime of x. I'm stopping at 0. Okay, stopping at 0, but I'm allowed to include 0. So that's nice. I have pi over 2. I have 3 pi over 2, and so I'm going to choose these numbers to plug into my derivative, of course being cos x, to see what type of value I get. So I'm going to plug in 0 because I'm allowed. I'm going to plug in 2 pi because I'm allowed, and it's going to give me the same exact thing. And I'm going to plug in regular pi because it's nice snugly in between. So f prime of 0 is cosine of 0, which is positive 1. So you're positive. F prime of pi is cos of pi, which is negative 1, negative. F prime of 0 is the same thing as f prime of 2 pi, so you're positive. So it looks like we are increasing on 2 intervals in between 0 and 2. So we're increasing between 0 and pi over 2. And we're also increasing at 3 pi over 2 and 2 pi. That would mean we're decreasing between pi over 2 and 3 pi over 2. So that gives us A. All right, fun stuff. Find the intervals where the function is increasing or decreasing. Now, the way you find out if something is increasing or decreasing is you take first the derivative and set it equal to 0 to find your critical points. Also, we care about where this guy is going to be undefined. So we're going to have a sign graph that involves probably 3 pieces of information, if not more. So let's take the derivative of this guy. And if you're thinking, is that quotient rule? Yes, it is. So u prime is going to be the derivative of the top, so 2x, not so bad. V prime is going to be the derivative of the bottom, which is 1, not so bad. And then v squared is going to equal x plus 1 squared. Quotient rule is u prime v minus v prime u all over v squared. So f prime of x is going to equal u prime v, so 2x times x plus 1, minus v prime u, which is going to be 1 times x squared minus 1, all over x plus 1 squared. Set it equal to 0. You're going to distribute that, so 2x squared plus 2x. You're going to distribute that, so minus x squared plus 1 all over x plus 1 squared. Let's multiply both sides by x plus 1 squared to make it go away, because we really don't need it. All right, boom. So 0 on the left, you're gone. We have 2x squared minus regular x squared is going to equal x squared plus 2x plus 1. That's going to be, oh, that's it. I was going to put all over something, but we're not going to put it all over something. That is a perfect square trinomial. So 0 is going to equal x plus 1 squared. So this is interesting. We have multiplicity going on here. Ooh, and not only that, but okay, let's take care of that thing first. Multiplicity, let's take care of that thing first. Multiplicity usually means something weird is going to happen. Okay, so 0, my number that's going to make that 0 is going to be -1. Coincidentally, the number that makes this is also, the number that makes it undefined is also -1. Huh. So I'm going to have a sign table where -1 is the only guy that I care about. So f prime, I could choose numbers like 0 and 100 and plug them into f prime. So if I plug them into f prime, okay, and I plug in 0, what did I get? That was f prime at its cleanest form. Let me just rewrite out f prime. F prime in its cleanest form was it was x squared because it was these guys plus 2x plus 1 over x plus 1 squared. So plugging in 0 would give me 1 over 1 squared, which is 1. So you're positive. Plugging in a huge number like 100 would be 100 squared, so a positive plus a big positive plus a positive all over a positive squared, which is a positive. So plugging in 100 also gives me a positive. Remember when I said that multiplicity is going to give us something weird? Well, this guy is never decreasing. So what we would say is it's increasing. Let me use a different color and write it over here where I have the space. It's going to be increasing at everything up until -1. So negative infinity to -1, and also -1 to positive infinity. And it's going to be decreasing never. Huh. Well, that's a strange problem. And this actually kind of does make sense. And let's just break it down why it will make sense. Just a quick picture. Okay? You got slant asymptote stuff going on here because this guy is greater than that guy. And the way you find the equation of a slant asymptote is you do polynomial long division. Polynomial long division is you basically saying, well, let's divide x plus 1, x minus 1 divided by x plus 1. That'll cross out, and so your slant asymptote is going to be y equals x minus 1. X minus 1. So you're going to have a picture with the slant asymptote that looks like this, right? And you're going to have something that looks like that and something that looks like that, which means at no point will it ever be decreasing. So you got a little bonus stuff there, but yeah, that's how you do that problem. Kind of weird, kind of fun. Given the function f of x equals x squared minus 6x plus 5, determine the type and location of the relative extrema. All right, well, this is what we're going to do. We're going to find our critical points. The way you find your critical points is you're going to do the derivative and set it equal to 0. So f prime of x equals 0, like that. F prime of x is going to be 2x minus 6. Set that equal to 0. Okay? Add 6, 2x equals 6, divide by 2. We have one critical point, and that critical point exists at x equals 3, which is all of these. So that didn't really help. Now, what I'm going to do is I'm going to make myself a sign chart or a sign graph or a sign table. And this is going to be for the derivative of x. Now, my magic number is 3. And so what I want to do is I want to find out where this graph is increasing and where this graph is decreasing. Okay, if I go from something that's increasing to decreasing, I have myself a relative maximum. If I go from decreasing to increasing, I have myself a relative minimum. And if I go from increasing to increasing or decreasing to decreasing, I have myself a neither. None of these are going to be inflection points. That's the second derivative. We'll get there. Now, the way I determine if something is increasing or decreasing is I choose a number in the interval that I care about. 3 is my only separation point. So I'm going to pick a number like 0, and I'm going to pick a number like 100. I'm going to take that and I'm going to plug that into the derivative. So the derivative that I got, and let me just write it out, the derivative that I got, since I messed it up all over here, was 2 times x minus 6. So if I plug in 0, I get f prime of 0 is going to be 2 times 0 minus 6, which is negative 6, which is negative. So you are a negative right here. If I were to plug in 100, f prime of 100 is going to be 2 times 100 minus 6, which is 200 minus 6, which is 194. That's positive. So you're positive. So what's happening is this is going down, and then all of a sudden we hit a 3, and now it's going up. So it looks to me that we have ourselves a relative minimum at x equals 3. Fun stuff. Given the function f of x equals x to the fourth minus 4x squared, determine the type and location of the relative extrema. All right, so this is what we're thinking, right? If we were to graph something, and if it goes from increasing to decreasing, we have a relative maximum. If we go from decreasing to increasing, we have a relative minimum. If we go from increase to decrease, those are the neithers. All right, so this is what we're going to do. We need to find the locations of the extrema, and you do that by finding out the critical points. Okay, the critical points are found by taking the derivative and setting it equal to 0. So the derivative of this guy up here is going to be power rule and power rule. So the derivative of f of x is going to be bring down the 4, x cubed, bring down the 2, minus 8x. Now let's set it equal to 0. Let's factor out a 4 and factor out an x, and that leaves us with x squared minus 2. Oh, I don't like that. So using the zero product property, I know that if I were to set 4x equal to 0 and divide by 4, I get x equals 0 is a critical point. If I take x squared minus 2 and set it equal to 0, add 2 to both sides, and then square root both sides, not forgetting the plus or the minus. So my other critical points are going to be positive or negative root 2 along with 0. So let's make a sign table for f prime of x. All right, my magic numbers are negative root 2, 0, and positive root 2. Now, in order where to find something is increasing or decreasing, I choose a number within these intervals. So like negative 1 fits in there, and 1 fits in here, and I can fit 100 here, and I can fit negative 100 here, although I'll probably regret those numbers, but that's okay. And then plug them in to the derivative, and if the derivative is positive, then it's increasing. If the derivative is negative, then it's decreasing. So let me take this formula right here. Okay, those negative hundreds I'm definitely going to regret, but you'll see what happens. It's actually not going to be bad at all. So let's do f prime of negative 100 and see what we get. Okay, f prime of negative 100 is going to be negative 100 cubed, 4 times negative 100 cubed, minus 8 times negative 100. So this is what you're going to get. Negative times a negative times a negative, or negative 100 times negative 100 times negative 100 is an insanely huge negative number. Multiply that by 4, but add 800 is going to keep it negative. So see what I did there? I don't really care about the number. I just care about the sign. F prime of negative 1 is going to be equal 4 times negative 1 cubed minus 8 times negative 1, which is going to be negative 1 cubed is negative 1. 4 times negative 1 is negative 4. Negative 4 plus 8 is going to be a positive number. 4 prime of regular 1 is going to be 4 times 1 cubed minus 8 times 1. So you get 4 minus 8, which is negative. And then you get f prime of 100, which is going to be 4 times 100 cubed, huge number, minus 800, which is going to stay positive. So this is what we're looking at. Negative, positive, negative, positive. Negative 2 is a relative minimum because it goes from negative to positive. 0 is a maximum because it goes from positive to negative. And square root of 2 is going to be a minimum again. So my relative minimum is going to happen at negative root 2 and positive root 2, like that says. And my relative maximum is going to occur at 0, like that says. The answer is C. Crazy. By the way, this is an even function. I just thought I'd share that. Thanks for watching. Let f be a polynomial function and the derivative of f is defined as f prime of x equals this guy right here. How many relative extreme points does the graph of f have? Ooh, tricky, tricky, tricky. Well, this is what I know. I know that if I wanted to find the critical points, you set the derivative equal to 0. Oh, happy day. The derivative is equal. Well, it's already the derivative, so I don't have to do much. That negative does nothing for me. X plus 1, x minus 1, multiplicity of 2, which means something fun's going to happen, and x minus 3. Whenever you have even multiplicity, something fun usually happens. My magic numbers here, according to the zero product property, are going to give me critical points at x equals negative 1, x equals positive 1, and x equals 3, exactly in that order. Now, 3 critical points does not mean I'm going to have 3 relative extrema. Okay, I have to graph. And again, that multiplicity of 2 is screaming my name. So I'm going to make a sign chart where I'm going to label negative 1, regular 1, and 3. What I'm going to do is I'm going to plug points in these intervals into that guy right there and see if I get positive, negative, or nothing. which that wouldn't happen. It'll either be positive or negative. If I go from increasing to decreasing, it's a max. If I go from decreasing to increasing, it's a min. And I go from positive to positive or negative negative, it's a neither. And again, that double multiplicity is screaming my name. I'm going to plug in negative 10. I'm going to plug in 0. I'm going to plug in 2. And I'm going to plug in 10. All right, so let's plug it into the original derivative right there. So f prime of negative 10 is going to be negative. So let's be smart here. Negative 10 plus 1 is going to stay negative. Negative 10 minus 1 is going to stay negative squared. And then negative 10 minus 3 is going to stay negative. Negative times a negative times a positive times a negative is going to stay negative. Okay, so you are negative. Let's plug in 0. F prime of 0 is going to be negative. Positive because 0 plus 1 is positive. 0 minus 1 is negative, but you're squaring it. 0 minus 3 is negative. So you become positive. So negative, positive, positive, negative is going to be positive. Let's try 2. Negative. 2 plus 1 is positive. 2 minus 1 is positive. Squaring it. 2 minus 3 is negative. So negative, positive, positive, negative is still positive. Ooh. Let's plug in 10. Negative. 10 plus 1. 10 minus 1. Square it. 10 minus 3. Negative, positive, 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 negative. So here, I go from negative to positive, keep going positive to negative. So I have a min right there, I have a max right there, and I have a neither right there. Ooh, so how many relative extreme points does this graph have? Not 3, boys and girls, but 2. Tricky, tricky, tricky. I like it. Given the function f of x equals x cubed minus 6x squared plus 9x plus 5, find the exact coordinates of the relative extrema. All right, so this is what I have to do. In order to find relative extrema, I have to find critical points first, and that's done by taking the derivative and setting it equal to 0 like so. All right, so let's do that. F prime is going to be power rule, power rule, power rule, power rule. So 3x squared minus 12x plus 9, nothing. Let's factor out a 3 and see what happens. That leaves us with x squared minus 4x plus 3, which continues factoring out to x minus 1, x minus 3. Okay, set that equal to 0. And we get nothing here that helps us out. X minus 1 gives us a 0 at positive 1. So positive 1 there, and at positive 3. All right, now that we have our critical points, we need to find out where this is increasing or decreasing so I can use that information to determine where the relative extrema exists. So 1 and 3 are my magic numbers, and I'm doing this with f prime of x. I'm going to plug these guys into actually probably that formula because it'll be easier to deal with. But I'm going to plug 0 because it's below 1. I'm going to plug in 2 because it's a nice number between 1 and 3. And I'm going to plug in 10 because that's nice. All right, so I'm going to plug it into u because the numbers will be nice. Okay, f prime of 0 is going to be 3 times 0 minus 1, which is negative 1, times 0 minus 3, which is negative 3. And all that ends up being 3 times negative, so it's going to be a positive number. I don't really care what the number is. I just care if it's positive or negative. Let's do the same thing with 2. F prime of 2 is going to be 3 times 2 minus 1, which is 1, 2 minus 3, which is negative 1. So positive times a negative is a negative. So you got yourself a negative right there. Let's plug in 10. F prime of 10 is going to be 3 times 9 times 7, all positives, give me a positive, everybody wins. So I know that since you go from increasing to decreasing to increasing, that you're going to be a relative max and you're going to be a relative min. But that's not good enough. I have to find the exact coordinates of the relative extrema, which means I have to take 1 and 3 and plug it into the original equation to get the actual values. So let's do f of 1 first. 1 cubed minus 6 times 1 squared plus 9 times 1 plus 5. That's going to get me 1 minus 6 times 1 plus 9 plus 5. So 1 minus 6 is negative 5, plus 5 is going to disappear, so we end up with 9. So what we have so far, and I'll write it down here in purple, is I knew that at 1, I get 9, and that's a relative maximum. So I have a relative max at the point 1, 9. Let's plug in 3 to see what our relative minimum is going to be, shall we? F of 3 is going to be 3 cubed minus 6 times 3 squared plus 9 times 3 plus 5. 3 cubed is 27. 6 times 3 squared is 6 times 9, which is minus 54. 3 times 9 is 27 plus 5. 27 and 27 make 54, which means all 3 of these guys cancel out. And so you get 5, which means my relative minimum is going to exist at the point 3, 5. And that is how you do it. Given the function f of x equals x cubed minus 6x squared plus 9x, find the x coordinates of the inflection points. Now, the inflection points exist when the second derivative is equal to 0. That's where change of concavity occurs. So let's find the first derivative. F prime of x is going to be power rule 3x squared, power rule negative 12x, power rule 9. The second derivative is going to be power rule 6x, power rule minus 12, power rule nothing. Set that equal to 0. 0 equals 6x minus 12. Let's add 12. Let's add 12. Cross you out. 12 equals 6x. Divide by 6. Divide by 6. X equals 2. So my one and only inflection point is going to be at x equals 2. Easy peasy lemon squeezy. Given the function f of x equals 2x to the fifth minus 5x to the fourth plus 10x cubed, find the x coordinates of the inflection points. Inflection points exist when f double prime, or the second derivative of x, equals 0. So we need to take the first derivative and take the second derivative, set it equal to 0, probably do some factoring, and then take it from there. So f prime of x, the first derivative is going to be power rule, so that's going to be 10x to the fourth minus power rule again, 20x to the third, plus power rule again, 30x squared. Now let's take the second derivative. F double prime of x is going to equal power rule 40x cubed, power rule minus 60x squared, power rule plus 60x. Now let's factor what we can factor. F double prime of x, I can factor out a 20, I can factor out an x, and that leaves me with 2x squared minus 3x plus 3. Now this is fun, because here we have an obvious point at x equals 0. Try to factor that out. You can't. See, if I set this equal to 0, which I forgot to do, so 20x, 2x to the second power minus 3x plus 3. If you do the zero product property, yeah, you get that x equals 0. You can't factor that out. That's not factorable. So I'm going to bring back an old friend called the quadratic formula. X equals negative b plus or minus square root b squared minus 4ac all over 2a, singing a song. You're my A, you're my B, you're my C. So x is going to equal negative 3 plus or minus the square root of negative 3 squared minus 4 times 2 times 3 all over 2 times a, which is 2 times 2. Now, let's write that out. X equals positive 3 plus or minus the square root of 9 minus 8 times 3 is 24. Now, that is a problem, because you're going to get the square root of a negative number. These are imaginary. Oh, no. So if these are imaginary, you only have one inflection point, because these are not real numbers. So my one and only inflection point is x equals 0. After all of that, lame city. But that's how you do it. If f double prime of x equals negative 6, then we may conclude that. All right, so what happened here is there must have been some f of x that was some type of polynomial. Then you do the first derivative, you get the second derivative, and you land on this. So what you're supposed to do is you're supposed to find inflection points. Well, finding the inflection points has you setting 0 equal to negative 6 and solving for x. There is no x, which means there's no inflection points. So basically what we have here is we are told that the second derivative is just a regular old negative number. Okay? In intervals where the second derivative is negative, tells us that it's concave down. So this entire derivative, second derivative, from negative infinity to positive infinity, is a negative number, which means it's concave down for all values of x. So kind of a strange problem, but that's what it means. If f double prime of x equals x minus 1 times the quantity x plus 2 cubed times the quantity x minus 5 squared, find the interval where f of x is concave down. Well, normally what you do is you take the function, you take the second derivative and set it equal to 0 to get your inflection points. This is already the second derivative. So I'm going to take this guy and set it equal to 0. Now here's the thing. Whenever we see multiplicity, that means something strange is going to happen. All right, so my inflection points are going to happen at x equals 1, negative 2, and positive 5. So we make ourselves a sign table for f double prime of x. And my magic numbers are negative 2, 1, and 5. We take numbers that are not within those, that are within the interval. So I'll take negative 10, plug it in. I'll take 0, plug it in. I'll take 3, plug it in. And I'll take regular 10, plug it in. And see if we get something that's positive or negative. Okay, in the intervals where it's positive, that means it's concave up. In the intervals where it's negative, that means it's concave down. So what I need to do is take all 4 of these numbers and plug them into my second derivative to see what I get. So f double prime of negative 10, I don't care about the actual answers. I just care if I get something that's positive or negative. So I'm going to have negative 10 minus 1, which is negative. Negative 10 plus 2, which is negative, squared, and negative 10 minus 5, which is negative, cubed. You become a negative times a positive times a negative, which is a positive. So this area is going to be positive, which means concave up. Okay, let's try it again for 0. F double prime of 0 is going to be 0 minus 1, which is negative. 0 plus 2, which is positive squared, and 0 minus 5, which is negative cubed. That's negative times a positive times a negative, which is interesting, positive. Now the reason why that's interesting is because we had even multiplicity. Oh, actually, no, that's odd multiplicity. Oh, super strange how that happened. Super strange indeed. So you're positive, which means you're concave up still. All right. F double prime of what else? 3 is going to equal 3 minus 1, which is positive. 3 plus 2, which is positive squared, 3 minus 5, which is negative. So I'm going to get a positive times a negative cubed, which is going to be a positive times a negative, which is a negative. So you are concave down. How nice. And then if I plug in 10, I'm going to get 10 minus 1, positive. 10 plus 2, positive. Squared, 10 minus 5, positive, cubed, giving me positive, giving me positive. So the only areas, the only interval where this is concave down is going to be between 1 and 5. That's it. So kind of a strange problem. But yeah, that's how you do it. If f prime of x equals x minus 1 times the quantity x plus 4 squared, find all values where f of x is concave up and increasing. So let's deal with that guy first. Okay, when something is increasing, what you do is you take the function, you find the critical points, and you find out where the derivative is positive. Okay, so I already have the derivative, so I can find the critical points. So the critical points are going to be found by setting this equal to 0, x minus 1, x plus 4 squared, and finding out what my critical points are by doing the zero product property. So x equals 1 will do it, and negative 4 will do it. So let's make a sign graph for f prime of x, and this will help me find out where this guy is increasing. So my magic numbers were negative 4 and 1. So what I can do is I can plug in negative 10, I can plug in 0, and I can plug in regular 10. So f prime of negative 10 is going to have me doing, and this is what I'll do. I don't care about the numbers. I care about whether it's positive or negative. So this will be negative 10 minus 1 is a negative number. Negative 10 plus 4 is also going to be a negative number. Square that. Negative times a positive is going to be negative. So you are negative. Okay, so not increasing there. Let's plug in 0. F prime of 0 is going to be 0 minus 1, which is negative, 0 plus 4, which is positive, squared, and a negative times a positive is a negative again. So there's no, there's a critical point, but there's no like max or min going on here because it goes from negative to a negative. But that's not what I'm supposed to do. I'm supposed to find out where this is increasing. So let's plug in 10. And that's going to be 10 minus 1, which is positive, 10 plus 4, which is positive, square it is positives all around. So you are finally increasing. So this is increasing on the interval 1 to infinity. Now I have to find concavity, which requires me to take the second derivative, and in this case I want concave up, finding out where it's positive. All right, so in order to do the second derivative, I'm going to use product rule. So u would be my u would be my v. So u prime would be the derivative of x minus 1, which is 1, and v prime would be, good old chain rule. So you drop down the 2, keep the inside, and then multiply everything by the derivative of the inside, which is just times 1, so I'm not going to change anything there. All right, so f double prime of x is going to equal u prime v, which is u prime, which is 1, times x plus 4 squared, plus v prime u, so 2 times x plus 4, u, which is x minus 1. Ugh. All right, so I'm probably going to have to do some foiling. Unless I want to do this instead. Watch what I do. This is me thinking outside the box. That one is not necessary. Okay, that one is not necessary. I have an x plus 4 and an x plus 4 in common with both, so let's pull it out. X plus 4. That leaves me with an x plus 4 here and a 2 times x minus 1. Okay, so by the way, that's f double prime. I don't know if I remembered to do a second thing there. Yeah, I think we're good. F double prime of x is going to equal x plus 4. So this will be x plus 2x, so 3x, and then 4 minus 2 is going to be plus 2. So setting that equal to 0, I have inflection points at x plus 4, 3x minus 2. Let's be cute here, negative 4. If I add 2, divide 3, I get 2/3. Okay, so let's make a sign chart involving the numbers for negative 4 and 2/3. So I can plug in negative 10, I can plug in 0, and I can plug in regular 10. Okay, so let's do the same thing that we did here with that guy and do f double prime of negative 10. That's going to be, if I'm going to use this equation right here, that's going to be negative 10 plus 4 is negative. Negative 10 times 3, that's going to be negative still. So a negative times a negative is a positive. So your positive, which is concave up, okay, I'll put positive because I'm trying to be consistent, not just the plus sign. Positive. If I plug in 0, f double prime of 0, I get 0 plus 4, which is positive, 0 minus 2, which is negative, so you're negative. And if I plug in 10, I get positive, and then 3 times 10 is 30. 30 minus 2 is still positive, so positive. So I want concave up. You're concave up here, and you're concave up here because of the f double prime sign graph. So I'm increasing from 1 to infinity, and I'm concave up from negative infinity to negative 4 union, and then 2/3 to infinity. So kind of a mess of a problem. And when I say kind of a mess of a problem, it's a mess of a problem, just like I am making a mess trying to circle it. But there you have it. Concave up here, increasing there, fun everywhere. Find the point of inflection of g of x equals x squared minus 8 over x as long as 8 is positive. Now, points of inflection exist when the second derivative is equal to 0. So this is what I need to do. I need to take the first derivative and then the second derivative, set it equal to 0, solve, see what happens. G double prime of, G single prime of x. Actually, and I'm not even going to do that yet. I have to rewrite this guy out. So G of x is going to equal x squared minus 8x to the negative 1. So I can use power rule and power rule. G prime of x is going to be 2x, pretty easy. Drop down the negative 1, multiply it to negative 8, giving you positive 8, x to the negative 2. G double prime of x is going to equal 2x, no, just 2, minus 16, x to the negative 3. Okay? Now, set that equal to 0. And I'm going to rewrite this back as 2 minus 16 over x to the third power. So probably the easiest way of handling this is by adding 16 over x cubed to both sides, so it looks like that, and then multiplying both sides to x cubed, like that. So then you have 16, and let's use a different color. 16 equals 2x cubed. Divide everything by 2. 16 is now 8, so let's not put 16 again. So 8 is equal to x cubed. Let's cube root both sides, and x is going to equal 2. So that's going to be u. So kind of a strange problem, but I liked it. I liked it a lot. Given f of x equals x cubed minus 3x squared plus 4, which of the following represents the intervals where the function is concave up? All right. So in order to find out if something is concave up, you need to take the second derivative and find the intervals where it's positive. So what I need to do first is take the first derivative. So f of x, or f prime of x, is going to be power rule 3x squared minus power rule 6x plus nothing. Let's take the second derivative, and f double prime of x is going to be power rule 6x minus 6. Now what we have to do is find our inflection points, and that's done by setting u equal to 0. So 6x minus 6. Add 6 to both sides, divide by 6, and my inflection point is going to be x equals 1. Now remember, inflection point means a change in concavity. So what I'm going to do is I'm going to make a sign chart for f double prime. I'm going to pick numbers like 0 and 10 and plug them into this formula right here to see if I get a positive or a negative number. A positive number means I get that concave up the way I want. A negative number means I get concave down. So if I plug in 0, f double prime of 0 is going to be 6 times 0 minus 6, which is negative 6, which is negative. Not what I want. F double prime of 10 is going to be 6 times 10 minus 6, which is 60 minus 6, which is 54, which is positive. And that happens at none of these. This happens from time to time where I try to get ChatGPT to make answers for me, and none of these are going to work out because the actual answer is going to be from 1 to infinity. So thanks a lot, ChatGPT. Your artificial intelligence, my foot. That's what I say. Thanks for watching. Like and subscribe. Given f of x equals 2x to the fourth minus 8x cubed plus 6, which of the following represents the intervals where the function is concave down? Well, in order to find out where something is concave down, you take the second derivative and find out where the second derivative is negative. In order to find the second derivative, we need to find the first derivative, which involves power rule, power rule, power rule. So you become 8x to the third minus 24x squared plus nothing. The second derivative is going to be power rule again, and that's going to be 24x squared minus 48x. Now what I need to do is find the inflection points, and the inflection points exist when the second derivative is equal to 0. So let's take this guy and set it equal to 0. 0 equals, let's factor out not only a 24 but also an x. So 24x times the quantity x minus 2. So my inflection points are going to be x equals 0 and x equals 2. So I'm going to make a sign graph for f double prime. 0 is a magic number, 2 is a magic number, and so what I'm going to want to do is plug in numbers in those intervals so I can find out where things are positive and where things are negatives in f double prime. So if I plug in -1, that'll be fine, and if I plug in regular 1, that'll be fine, and if I plug in 3, that'll be fine. So f double prime of -1, if I use this guy right here, which seems to be a little bit easier, so I'm going to use that, so that is still f double prime. I'm going to get 24 times -1, so negative 24. I'm going to get -1 minus 2, which is -3. And I don't care what number I get. I just know that this is positive. So you're going to be positive right here. So not at all what I want. F double prime of regular 1 is going to be 24 times 1, which is 24. and 1 minus 2, which is negative 1. 24 times negative 1 is negative 24, which is negative. So far, you are what I want, to quote a song from Greece. F double prime of 3 is going to be 24 times 3, which is 72. And 3 minus 2 is 1, so that's going to become positive, so you're going to become positive. So you are where we're concave down, between 0 and 2, which is B. Okay? So yeah, that's how you do it. Fun stuff. Given f of x equals negative x to the third plus 6x squared minus 9x, where is the function concave up and concave down? Well, my function is going to be concave up when the second derivative is greater than 0. It's going to be concave down when the second derivative is less than 0. So what I need to do in order to find the second derivative is I need to find the first derivative first. So f prime of x is going to equal power rule. Negative x cubed becomes negative 3x squared. Positive 6x squared is going to become plus 12x. Minus 9x is minus 9. Now my second derivative is going to be power rule again. So f double prime of x is going to be negative 6x plus 12 plus nothing. Okay, so what I have to do is I have to find my inflection points. My inflection points exist when f double prime of x is equal to 0. Okay, and I'm going to have one inflection point, negative 6x plus 12. I'm going to have one inflection point, and that's going to happen at, well, let's see, minus 12, negative 12 equals negative 6x, divide by negative 6, divide by negative 6, x equals 2. So what I can do is I can make myself a sign chart for f double prime. 2 is my magic number. What I need to do is I need to find out where my second derivative is positive and where my second derivative is negative. I know it's 0 at 2. So if I were to take, like, I don't know, 0 and plug it in, or if I were to take 10 and plug it in, that'll help me figure out if this is positive or negative here, or if this is positive or negative here. So f double prime of 0 is going to involve me taking this guy right here and substituting in 0. Negative 6 times 0 plus 12 equals positive 12, which means you are positive right here. F double prime of 10 is going to be negative 6 times 10 plus 12 is negative 60 plus 12, which is like negative 48, so definitely negative. So if your second derivative is positive, that means you're concave up. If your second derivative is negative, that means you're concave down. So we could say that we are concave up on the interval negative infinity to 2, and we can say that we're concave down on the interval 2 to infinity. And this makes sense. This is a cubic. Cubic looks like this. So at some point here, and that point is going to be 2, we go from concave up to concave down. And I know this cubic looks like that because of the negative in front of x cubed. So it all checks out. It all checks out, baby. Given f of x equals x to the fourth minus 6x squared plus 16, where is the function concave up and where is it concave down? Well, a function is concave up when your second derivative is positive. It's concave down when your second derivative is negative. So in order for me to find second derivative, I have to find my first derivative first, and that's going to involve power rule a couple times. Drop down the 4x cubed. Drop down the 2, multiply it to negative 8, negative 8, 16, x. 16 becomes nothing. Okay, let's find the second derivative. F double prime of x is going to be 4 times 3, which is 12x squared, and then you become minus 16. Ugh. This is going to be gross. That grunt means it's not going to be pretty at all. Okay, so inflection points. Inflection points exist when the f double prime of x is equal to 0. Okay, so that happens when 12x squared minus 16 equals 0. So let's add 16 to both sides, like you, and you get 16 equals 12x squared. Divide everything by 12, divide everything by 12, you get 4/3 equals x squared. Square root, don't forget your positive or negative, and you have two inflection points. Okay, my inflection points exist at the square root of 4 is 2, so they exist, is that supposed to be x? I don't know what I did there. They exist at negative square root of 4 is 2 over root 3 and positive 2 over root 3. So let's go up here and make ourselves a sign chart for f double prime. Okay, my magic numbers are 2 over root 3, negative, and 2 over root 3, positive. So if I pick a number like negative 10, if I pick a number like 0 and positive 10, I should be able to plug it into this guy right here and see what I get. So a little bit of math to do here. It's not going to be a ton of fun. F prime of negative 10 is going to be 12 times negative 10 squared minus 16. So 12 times 100 minus 16. Now, I'm not going to freak out about the numbers. I know 12 times 100 is 1200. 1200 minus 16 is a positive number. So you are going to be positive here on f double prime, which means you're going to be concave up because it's positive. So I drew the concave up. I don't know why I did that, but I'm sticking with it. I'm leaving it there. Let's plug in 0. F prime of 0 is going to be 12 times 0 squared minus 16, which is going to be negative 16. You're negative, which means you're going to be concave down. If I plug in positive 10, f double prime, and these are all double primes, f double prime of 10 is going to be 12 times positive 10 squared minus 16, which is going to give us the same exact thing as up here. So you're also going to be positive. So you're positive, concave up. So we could say that this function is concave up on two intervals from negative infinity to negative 2 over root 3 union positive 2 over root 3 to regular infinity. It's going to be concave down in between those two gross numbers. So negative 2 over root 3 to positive 2 over root 3. And when we close that off, we get ourselves an answer, and that is how it's done. Gross. Given f of x equals x to the third minus 3x squared plus 4x and the critical point x equals 1, use the second derivative test to determine the type of relative extrema at x equals 1. Well, this is how the second derivative test works, right? Second derivative gives you concavity. So if second derivative is a positive number, that means it's concave up, which means at whatever point you're talking about, you're going to have yourself a relative minimum. Okay? If you take the second derivative and your number is negative at that point, you're going to have something that's concave down, which means that point is going to be a relative maximum. If it's equal to 0, I'm sorry, you've got nothing. Okay, you've got yourself a good old inflection point. Okay, because it's neither. Okay? So, what we have to do is we have to take the second derivative. So f prime of x is going to involve us using the first derivative. So that's power rule once and power rule twice and power rule 3 times. F double prime of x is going to be 6x minus 6. Now what I do is I take my point, right, x equals 1, and I plug that into f double prime of x. So 6 times 1 minus 6 is 6 minus 6. It's 0. It's an inflection point. Oh, duped. We got duped. But that's how you do it. Given f of x equals 3 over x squared plus 4x and the critical point x equals -2, use the second derivative test to determine the type of relative extrema at x equals -2. Well, what I know about the second derivative is that if it's positive, right, it's concave up. So at some point c, right, if I plug it in, that's going to give me a relative minimum. If I have something that's negative, it's concave down, which means at some point c, it's going to be a maximum. If my second derivative is 0, well, that's an inflection point. It's neither of them. So let's take a look at this guy, and let me rewrite it out in a much friendlier way so I can just do power rule. I'm going to turn 3 over x squared into 3x to the -2, and then add 4x, and then take the derivative of that guy. So f double prime, a regular prime rather, of x is going to be -6x to the -3rd plus 4. F double prime of x is going to be -6 times -3, which is positive 18. That was a close one. Positive 18, x to the -4 plus nothing. So if I care about -2, then let me rewrite this out. F double prime of x equals 18 over x to the 4th. Plugging in -2 is going to be 18 over -2 to the 4th, which is going to be 18 over -2 times -2 times -2 times -2, which is 16, which is going to be a positive number. So since it's positive number, we have something that's concave up, which means it's going to be a relative minimum. Second derivative test, so much fun. If f prime of 8 equals 0 and f double prime of 8 equals 3, which of the following must always be true? Well, f single prime of 8 means that x equals 8 is a critical point. Okay. F double prime of 8 being positive means that my second derivative being positive is it's concave up. And it's concave up at a critical point, which means that's a relative maximum or minimum. So in this case, what I have is I have a relative minimum at x equals 8. Quick and painless. Given f of x equals x to the 3rd minus 6x squared plus 9x, determine all relative extrema. Well, this section uses the second derivative test. So what I want to do is I want to find all critical points, okay, and we'll call them C. For any critical point C, if f double prime of C is positive, that means it's concave up and I have myself a relative minimum. If f double prime is negative, that means I'm concave down and I have myself a relative maximum. All right, so let's take the first derivative and find out my critical points. So f prime of x is going to be 3x squared minus 12x plus 9. Let's set it equal to 0 and pull out a 3, and that's going to be x squared minus 4x plus 3. Factoring this further, I have 3 times x minus 3, x minus 1. So my critical points exist at 3 and 1. Those are my critical points. I'm going to take those guys, and I'm going to plug them into the second derivative, which I haven't found yet. So if the first derivative is 3x squared minus 12x plus 9, the second derivative is going to be 6x minus 12. So f double prime of, let's go in order, of 1 is going to be 6 times 1 minus 12, which is 6 minus 12, which is negative. If it's negative, that means I have, at 1, a relative max. F double prime of, what's the other one, 3, is going to be 6 times 3 minus 12, which is 18 minus 12, which is positive. So at 3, Since it's positive, I have a relative minimum. So determine all relative extrema. Relative extrema at x equals 1 and 3. Kind of a lazy answer. But these are the specific relative extrema, so I kind of took it a step further, even though technically I could have stopped right there. But I'm happy with what I did. I'm keeping it. Can't stop me. Given f of x equals 2x to the fourth minus 2x cubed plus 6x, determine all relative extrema. We are using the second derivative test for this. So this is what we have to do. Step 1 is we have to find all of our critical points. Okay, so any critical point we'll call C. Step 2 is once we have that, we throw that into the second derivative. If it's positive, that means it's concave up, and at that C, we have ourselves a relative minimum. If we plug in that C, which represents a relative maximum or a minimum, and it's negative, that means it's concave down. And at that moment, we have a relative maximum. So what we have to do is we have to find the first derivative first. So f prime of x equals 2 times, actually it's going to be 8, sorry, 8 x to the third minus 24x squared plus nothing. Let's set that equal to 0 to find our critical points. Let's factor out an 8x squared, and that leaves me with x minus 3. Okay, now multiplicity of 2 scares me a little bit, but I still get x equals 0, and I get x equals 3. Now what I haven't figured out yet is what f double prime is. So f double prime of x is going to be 24x cubed minus 48x. And with that scaring me a little bit, with that multiplicity of 2 scaring me a little bit, that's going to remind me that f double prime of c, if it equals 0, is going to be an inflection point. Okay, so neither of that. Neither of that. But we'll see if we have to worry about that. We might. So I have 0 and 3. So f double prime of 0 is going to be 24 times 0 cubed. Remember a second ago how I said that we'll see if we have to worry about it? Well, guess what we just got? We just got an inflection point, which is not a type of extrema. So 0 ain't it. F double prime of 3 is going to be 24 times 3 cubed minus 48 times 3. That's going to be 24 times 9 minus 48 times 3, which is going to be, I don't know, 200 something minus like 100 something. So based off of that information, I'm just going to say it's positive because it is. So f double prime of 3 being positive tells us that we have a relative minimum at 3. So the relative min is going to exist at x equals 3. That's how you do it. The graph of the function f is shown in the figure to the right-ish. For which of the following values of x is f prime of x negative and decreasing? So if f prime of x is negative, that means it is going down and to the right. It has a negative slope. So this part means negative slope. When it's decreasing, if the slope is decreasing, that implies concave down. When the rate of change is decreasing, concave down, if you remember that from AP pre-calculus. So I need something that has a negative slope and is also concave down. So A has a negative slope and appears to be concave down. B, nothing. C is positive and concave down. D is negative and concave down, and A is positive and concave up. Oh, no, I take it back. D is not concave down. D is an inflection point. So the only guy that I can choose is A. because A is the only spot that is concave down and also decreasing. So kind of a bizarre problem. Boy, does that look awful. But I did it. Given the graph of f prime of x, determine which of the following statements must be true. All right, so this is f prime of x, not f of x. So let's look at these three options. Option number one says relative minimum at wherever. Well, in order for there to be a relative minimum, that means our derivative, right, must go from negative to positive. So if at negative 7 over 4, which appears to be u, I'm going from negative to positive. So that's a 0. This is negative, this is positive, so this is true. If f of x is concave down at negative 2, 2, that means that the rate of change, or the slope, if it's concave down, the slope is decreasing. At negative 2, 2. So here's negative 2. There is no negative 2, 2. Oh, it's talking about this guy. It's talking about the interval. It's talking about the interval negative 2, 2. Well, my slope this whole way is positive, getting shallow, getting more shallow, getting more shallow, getting more shallow, getting more shallow, negative, bigger negative, steeper negative, steeper negative, steeper negative, steeper negative. So yeah, since my rate of change is decreasing the whole time, we could say 2 is true. F of x is differentiable on the interval negative 3 and 3. That is not true because we have a sharp edge right here and a sharp edge right here, which means it's not going to be differential at those two areas. So the only ones that work are 1 and 2. The graph of the derivative of function f is shown below. At what value of x does function f have a relative maximum? Okay, so this is the derivative. A relative maximum occurs when your derivative goes from positive to negative, because that would represent a relative maximum. What I need to do first is find out the critical points for that to happen. So since this is the derivative, I care about where I get a 0, which is negative 2 and at 1. So I can make a sign chart of f prime of x based off of that information. At negative 2 and at positive 1. To the left of negative 2, I'm in positive land. And at negative 2 to 1, I'm below the x-axis. And from 1 on, I'm also below the x-axis. So right here at negative 2, I go from positive increasing to negative decreasing, which means I have a relative maximum at that guy right there, negative 2. So that's how you do it. The graph shown below shows the derivative f prime of x of the function f of x. At which values does function f have a point of an inflection? Well, a point of inflection exists when f double prime of x equals 0. Now, what that would mean in this context is that the derivative of this function is 0, which means I want a slope of 0 or a flat slope. Where does that happen? Well, it happens at B, where it changes from positive to negative, and it happens at D, where it changes from negative to positive and nowhere else. So B and D are going to have a horizontal slope, which means the derivative of the derivative is 0 at B and D. Interesting problem. I like it. The graph of the function y equals f of x is shown below. On which of the following intervals is f prime of x greater than 0 and f double prime of x greater than 0? If f prime of x is positive, that implies that is increasing function. Okay, increasing function. It doesn't matter what it looks like as it's increasing, as long as it's going up and to the right, it's increasing. If f double prime is greater than 0, that implies that it's concave up. So I need both. I need a part that's both concave up and increasing. I think the easiest thing to do first is maybe find the concave up part, so maybe I'll do that, and that appears to be happening between A and C, so you are concave up right here in that nice big purple, oh boy, purple line. And while that's concave up, it's also increasing between just B and C, right? So where that's happening with both is going to be in between, but not including B and C. So ignore the brackets here. We'll quick turn them into parentheses so no one screams at me in the comments, which no one really does anyway. They just gently tell me where I went wrong. So only between B and C. So between C and D, no. Between A and B, no. Between B and C, yup. And so we're going to say 3 only for that guy. Okay, that's where I want both of those things to occur, and both of those things occur only in between B and C. Dunzo. An equation of the line tangent to the graph of f of x equals 2x cubed minus 3x squared at its point of inflection is which of these? Ugh. All right, so what we have to do first is we have to find the point of inflection. And the way you find the point of inflection is you find out when f double prime of x is equal to 0. So let's find out what f double prime is. First, we have to find out what f single prime is, so let's get rid of you. F single prime of x is going to equal, drop down to 3, 6x squared, drop down to 2, minus 6x, that's f single prime. F double prime is going to be the derivative of that, and that's going to happen at 12x minus 6. All right, so set it equal to 0. 0 equals 12x minus 6. Let's add 6 to both sides. That gets me 6 equals 12x. Divide by 12, divide by 12. And the point of inflection occurs at x equals 1/2. Now, in order for me to come up with an equation of anything, right, I need a point and I need a slope. I have half a point. So the way I find the other half a point is I take that 1/2, I plug it into the original function, and that'll give me the f of x or the y value of the other half a point. So I need to find out what f of 1/2 is. So f of 1/2 is going to be 2 times 1/2 to the third minus 3 times 1/2 squared. Okay. Let me see. So that's going to be f of 1/2. My y value is going to be 2 times a half times a half times a half is 1/8. Minus 3 times a half times a half is a fourth. That simplifies out to 2 times 1/8 is a quarter. Minus 3/4 is going to be negative 2/4, which is negative a half. So we have a point, and that point is 1/2, negative 1/2. Now I have a point. What I don't have is a slope. The way I find my slope of the tangent line is I take my derivative and plug in that 1/2. So here was my derivative, so let me bring that down over here. Let's plug 1/2 into that. So f prime of 1/2 is going to be 6 times 1/2 squared minus 6 times 1/2. Okay, that's going to be my derivative at the x value 1/2. That will give me 6 times a quarter, because a half squared is a quarter, minus 3. That will get me the 6 to 3, 6/4 minus 3 is 3/2 minus 3, which is negative 3/2, so negative 1.5. Ugh. So that's my slope. So I guess what I'll do is I'll plug this into point slope form. Y minus y sub 1 equals m times the quantity x minus x sub 1, and I'll turn that into standard form, which is what they want. So what color didn't I use yet? Green. Y minus, you're my y sub 1, so minus negative means plus a half, equals m is negative 3 over 2 times the quantity x minus x sub 1, which is minus a half. Let's distribute that to give me, and I'm just going to write left to right, I guess. Y plus a half equals negative 3 over 2x plus 3 over 4. Ugh. Boy, I don't like that at all. What I'm going to do is I'm going to add 3 over 2 to both sides. So I'm going to put 3 over 2x, rather, plus y to both sides, right? I'm going to subtract a half here, which gives me a quarter. And they want all constants here, so if I multiply everything by 4, that gets rid of all fractions. So 4 times 3 over 2 is going to be 6x plus 4y equals 1. Tricky, tricky, tricky. Kind of tough. Didn't like it. The graph of y equals f of x is shown below. If f is twice differentiable, which of the following is true? Well, it's giving me information about what f of x is, what f prime of x is, and what f double prime of x is. F of x tells me where it is above or below the x-axis, right? So let's say that as part 1. Part 2, the derivative tells me if it's positive or negative, whether it's increasing or decreasing. Why I abbreviated increasing but not decreasing, don't ask. This guy is telling me the second derivative, whether it's concave up or concave down. So it won't abbreviate. Well, I did abbreviate both of those. Now let's find out what we have in blue first. This is above the x-axis, right? The whole thing. So we know that f of x is going to be above the x-axis, so f of x is positive, which eliminates u. Now, this whole function is going down and to the right, which means it's decreasing, which means f prime of x is less than 0. Okay, which eliminates u and eliminates u. This function is concave up, which means f double prime is positive, which eliminates u and gives me u. So B is going to be my answer for that one. Fun stuff. A manufacturer is designing a rectangular garden that is to be enclosed with a fence. The company has a budget that allows for a maximum perimeter of 60 meters. So perimeter of a rectangle is 2 times length plus 2 times width. Has to have a maximum perimeter of 60 meters, so it's got to be less than or equal to 60. The garden must also meet the following real-life restrictions. The width of the garden cannot exceed 15 meters due to space limitations. So we'll call this the width, okay? It cannot exceed 15 meters, which means it's got to be 15 meters or less. All right. The length of the garden must be at least 5 meters to ensure adequate growth space. So length has got to be greater than or equal to 5. All right. Which of the following measurements for the width of the garden cannot be used due to real-life restrictions? So what we'll do is we'll go through the list, we'll plug stuff in, and we'll see what happens. All right. So A is going to have me plugging in 10. And by the way, width, that's the key here. We're talking about width. So I'm going to plug in 10 for W. So 2L plus 2 times 10 has to be less than or equal to 60. Okay, and while doing this, we are trying to make sure that our length is greater than or equal to 5. So 2L plus 20 is less than or equal to 60. Quick math, I'm not going to show my work. Subtract 20, 2L is less than or equal to 40, right? divide by 2, L is less than or equal to 20. So this gives us a box that follows the rules where I would have a width of 10, which is fine, and a length of 20, which is good. And so my perimeter would still be 60. All is well. No complaints here. You check out. You are not a problem. If I were to try 5, I would do the same process. 2L plus 2 times 5 has got to be less than 60. Okay, so 2L plus 10 has to be less than 60. 2L, subtract 10 from both sides, is going to give you 50, right? Divide by 2, the length is going to be less than or equal to 25. So that gives us a box of 25, 25, 5, and 5. It's less than 25, which is greater than 5. Everybody's happy, everybody's good, no problem, we can do it. 5 checks out. And then we get to C and realize, boy, oh boy, did we waste our time. Because it says here that this is the width. The width can't be bigger than 15. So why in the world could it be 20? Well, all right. So, again, the point of this was for me, I showed my work anyway in the off chance this problem wasn't as complicated as it was. In this case, it's not complicated at all. I mean, the answer is screaming at you right there. 15 is going to work, trust me, but 20 is already telling you, yeah, it can't work based on these restrictions right here. So that's optimization. With optimization problems, and this is the intro to optimization, you are looking at restrictions when building real-life objects, and 20 screams at you that, yeah, that's a restriction. So much easier than it had to be. I just like to complicate things. I'm like Avril Lavigne, and why did I have to go and make things so complicated? Remember that song? You probably don't. You were too young. Thanks for watching. Like and subscribe. Your company has given you the task of creating an open box with a square base to be used for packaging. So we draw a picture, and I don't know what I'm doing, so that's the best I can do. The specifications for the box include using a 432 centimeters squared of cardboard and a maximum width of 20 centimeters. Great. You have created a differentiated volume function and found that the only crucial value, or I guess critical point, occurs at x equals 12. Interesting. The values of v prime, the derivative of the volume function, are shown in the table below. Based on the data in the table, what width should be used to maximize the volume? Now, whenever you're looking for maximum and minimums, right, in this case, we're looking for a maximum, you're thinking of a relative or local maximum, or in this case, local minimum if I wanted to add to it. Now, that happens when you know you're going from increasing to decreasing or decreasing to increasing, which means that happens when your derivative goes from either positive, so we'll say v of prime, goes from positive to negative, or negative to positive. So the devil is going to tell you, select this one, 81's the maximum, but that's actually not what you're doing. You are building yourself a sine graph because you're given v prime. These guys give you critical points, not maximum volume. Maximum volume is used by finding or by plugging stuff into the volume formula, not the derivative formula. So this is a critical point right here because it's 0, and this is a critical point, which means it's 0. So if I put what I have, I can put an 8 here, and I can put a 18 there. Based on my derivative, you're a positive number, which means between 8 and 18, I'm increasing. Okay, you're a negative number after 18, which means after 18, you're decreasing, which means a maximum occurs right there at 18. So since my maximum value occurs at 18, the maximum number is going to occur, the maximum volume is going to occur when x equals 18. So again, I think most people would look at this problem and assume that the answer is 12 because 81 is bigger than all these numbers here. But since we're given v prime, that is not what we're doing. V prime gives us the location of the maximums and the minimums, and those locations exist when it equals 0. So kind of a tricky problem, but I had fun. A manufacturer wants to create an open box by cutting out x-sized squares from each corner of a rectangular piece of cardboard measuring 10 by 20 centimeters. So let's do our best to try to draw that picture right here. Okay, so we have a rectangle. You would be 20, you would be 10. I am cutting out x-sized shapes, x-size squares, right, out of each corner. So x, 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 x. Now, what that does is the brand new length of these guys are going to be whatever this length is, 10 minus 2x. This length is going to be 20 minus 2x. So common sense would tell us that, like, I couldn't say, well, let's cut out 7 sized x's. Well, that doesn't make sense, because if you choose 7, then you would get 2 times 7 here, which is 14, and 10 minus 14 means you're going to have a length of rectangle that is -4. That doesn't make sense. So one of these will not work, and that's the problem. After cutting these squares, the sides of them are folded up to form the walls. Great. Which of the following values cannot be used due to real-life restrictions of the dimensions of the box? Well, let's say you weren't thinking and you decided, well, let's go and test all of them out. If I were to cut out x-sized shapes, that means the length or width, whatever you want to call it, would be 10 minus 2 times 2, which is 4. So that would give us a box, right? That would give us a box with a height or whatever of 4. Actually, the height would be x, so we would call u4. Can I move the 4? Yeah, no problem, no problem, no problem, no problem, no problem. And what would u be? U would be 20 minus 2 times 2, which is 4, so u would be 16, 16, everything's fair. But then common sense takes over and says, well, wait a minute. Why don't I pick this 5? Because if I decide to cut out 5 shaped x's, then this is going to be 10 minus 2 times 10, which is 0. So that means I'm going to have a box with, boy, am I awful at drawing these. I'm going to have a box, I give up. I'm going to have a box with a length of 0. Well, that can't happen. That's not a box. It's invisible then. So we decide C has got to be our answer, because C cannot work. Because if I plug in 5 for C, or 5 for X, I get 10 minus 10, which is nothing. So I don't have a box anymore. Stinks. So optimization, you're looking for things that can't possibly work, and that was one of them. Fun, fun. A farmer has 200 meters of fencing to create a rectangular enclosure. What dimensions will maximize the area of the enclosure? So this is the idea of optimization problems, which is 511 here. The idea behind an optimization problem is you are trying to take an equation, take the derivative of it, giving you critical points, and critical points give you a local maximum or a local minimum. So let's start out with what we know. We have a rectangular fenced-in area, so this is me doing the best I can drawing a rectangle, and I did a decent job here. We'll call you length and width. And we know that we have 200 meters to work with. So using the information we learned from elementary school, 2 times length plus 2 times width is equal to 200. That's my perimeter formula. Now, what I'm also trying to do is maximize the area. So another equation that I could use is A equals length times width. Now, my job is to maximize this, which means I want to take the derivative of that. Right now, I don't want to because there's 2 different variables. Oh, but since I have this equation, I could solve this equation for like L or W, plug it into that guy, and I only have 1 variable to deal with. So let's do that. Let's solve it for W. Let's subtract 2L, cross U out. 2W equals 200 minus 2L, like so. Divide everything by 2, divide everything by 2, divide everything by 2, cross U out. W equals 100 minus L. So now what I can do is I could take that equation and that information and create a brand new equation. Even though I put the arrows there, I'm going to put it way over here. A is going to equal, instead of, well, I'm going to keep LL, and instead of W, I have 100 minus L. Distributive property tells me that A is going to equal 100L minus L squared. Now let's take the derivative of that. A prime is going to equal 100 minus 2L. In order to find the critical points, you set it equal to 0. So 100 minus 2L Let's add 2L to both sides. So let's move this up here. 2L equals 100. And my one and only critical point is going to happen at 50, which means 50 exists at a maximum or minimum. And in this case, it's going to be a maximum because the numbers make it work that way. Now, if the length is 50, I need to find the width. Up here, it says that the width is 100 minus L. So the width is going to be 100 minus 50. So the width is 50. My job is to maximize the area. Area is length times width. So area in this case is 50 times 50, which is 2,500. So it's going to be A. Now, a fun fact, if you're given a rectangle and all four sides to make fencing out of, your maximized area is always going to be a square. Always, always, always. Now, later you'll see me do a problem where I have the fencing holding up against a barn, where I only care about 3 sides. That's not going to be the same. But in this case, we get a square, and that makes sense. Yes, the old open box volume problem. You will see this in every calculus class. A manufacturer wants to create an open box by cutting out squares of size x from each corner of a rectangular piece of cardboard measuring 8 by 10. So, there's my cardboard. This is me cutting out an x, cutting out an x, cutting out an x, cutting out an x, 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 x is everywhere. X is everywhere. Now I know that one of these sides is 10 and one of these sides is 8, which means after I cut things out, you're going to be 10 minus x, so 10 minus 2x, and you're going to be 8 minus x, so 8 minus 2x. When I take these sides and fold them up, that gives me a box with an open top, right? Where the height is going to be x, the width is going to be 8 minus 2x, and the length is going to be 10 minus 2x. So this is where the fun begins. My job, after cutting the squares, the sides of the box will be folded up to form the walls. Yeah, I kind of got that. What size x squared should be to maximize the volume of the box. So this is where it gets tricky. The volume of the box is going to be x times 10 minus 2x times 8 minus 2x. Okay, so let's multiply stuff out. The volume is going to be 10x minus 2x squared times 8 minus 2x. Let's FOIL stuff out. 80x minus 20x squared minus 16x squared plus 4x to the third. And that's my volume formula. Now what I need to do is I need to take that volume formula and take the derivative of it. That's going to help me find maximum or minimum values. Okay, so the derivative, actually, you know what, let me clean this up a little bit. Let me put it in order, put it all together. That would probably be a smarter idea. 4x to the third minus 36x squared plus 80x. Okay, and I got that negative 36 by combining these guys right here. Now I'll take the derivative. When I take the derivative, that gives me 12x squared minus 72x plus 8. Set it equal to 0 to get me critical points. And what I'm also going to do while I set it equal to 0 is factor out a 4. 3x squared minus 18x plus 20. Now, the frustrating things about these types of problems and what we're left over here is you can't factor that. It's a mess. So we're going to use our dear friend, the quadratic formula. I'll call you A, I'll call you B, I'll call you C. X equals negative B plus or minus square root B squared minus 4AC all over 2A. And we'll plug in our friends. Negative 18 plus or minus, the square root of negative 18 squared minus 4 times A, which is 3, times C, which is 20, all over 2A, which is 2 times 3. All right, so the double negative 18, 18. plus or minus 18 squared is 324. Took me a minute there. Negative 4 times 3 is 12 times 20 is 240, but the negative version of it, all over, that'll be 6. This guy simplifies out to 84, all over 6. You can pull out a 4, which means you can pull out a 2, so 18 plus or minus 2. If you get rid of the 4 in there, you're left with, oh, no way, my favorite number, 21, all over 6. Now, I'm going to quick run to a calculator and type out what this guy is. Oh, by the way, no, I won't. 9 plus or minus the square root of 21 all over 3, because I can simplify all those even numbers. Now I'm going to go off to the side and see what I get. All right, so I got x equals, give or take, 4.53 and 1.47. One of these numbers can't make sense, and it's u. U can't make sense because if I were to say, all right, yeah, let's cut out 4.53 out of this thing, you would have 8 minus like 9, which means you would have negative box. That doesn't make sense. So our only feasible option is that 1.47. So that's the only guy we're going to be able to get. Tricky stuff. Quadratic formula is never fun, but you need to know how to use it, so this is us using it. Happy times. A farmer wants to create a rectangular fenced-in area against the side of a barn. The farmer side of the barn, rectangular fenced-in area. The farmer has 40 meters of fencing available and will use the side of the barn as one side of the rectangle. Let x be the length of the rectangle perpendicular to the barn, so u, and y be the length parallel to the barn, so u. Okay. And again, our job is to maximize the area. Okay, so when you have a problem like this, you need to come up with as many equations as you can. I have 2 x's and a y giving me a perimeter of 40. So there's my perimeter formula. Okay, I'm also supposed to maximize the area, so the area is going to be x times y, which means I'm going to want to take the derivative of this. But I can't because I have 2 variables. Oh, but you know what? Since I have this information, I could just subtract 2x minus 2x like so, get y equals 40 minus 2x, and then replace that y with 40 minus 2x, and then I have 1 variable. So a is going to equal 40x minus 2x squared. Now we take the derivative of that, because taking the derivative will allow us to find critical points, which gives us maximums or minimums. Okay, so a prime is going to equal 40 minus 4x. Set it equal to 0 to find my critical point, so 40 minus 4x is equal to 0. Add 4x, and 4x will equal 40. Divide by 4, x is 10. And if x is 10, that means I could use that equation right here to find out that y equals 40 minus 2 times 10, which is 40 minus 20, which is 20. So y is 20, x is 10, even though I wrote 0, 10, and 20 gives us the answer of A. Now, in a previous problem, you saw me do one where I gave you all 4 sides of the fence. That answer was a square. This one's not, because I'm not using all 4 sides of the fence. Fun stuff. The amount of food in grams consumed by a goldfish each day during its lifespan of 20 days is modeled by the equation f of t equals negative 0.1 t squared plus 2t plus 20, where t is the number of days. During which day will the goldfish consume the most grams of food? So we need to maximize this guy right here. Well, in order to maximize something, we need to first take the derivative. So I'm going to take the derivative, and that's going to be drop down that 2, negative 0.2 regular t plus 2 plus nothing. In order to maximize it, we set it equal to 0 to find our critical point. So 0 is going to equal negative 2t plus 2. Let's add 0.2t to both sides, add 0.2t to both sides, so I have 0.2t equals regular 2. Let's get a different color in here because why not? Divide both sides by 0.2, divide both sides by 0.2, and t equals 10, my only critical point, which means the time 10, or in this case day 10, is when Mr. Goldfish is going to consume the most food. Good for you, Mr. Goldfish. Live your life. If x squared y plus y squared plus 4 equals 0, then when x equals 2, the value of dy dx is. So we're going to have to use implicit differentiation and ddx both sides. So ddx of x squared y plus y squared plus 4 equals 0. So this involves power rules. So u is x squared, v is y. U prime means taking the derivative with respect to x of x squared, which is 2x. The derivative of y with respect to x is 1 dy dx. Now that's v prime. Okay. Product rule is u prime v, so x squared dy dx. Oh, I have that backwards. Actually, it wouldn't make much of a difference, but if I'm going to be consistent, I want to be consistent. U prime v is 2xy plus v prime u, which is dy dx x squared. That was just this part, by the way. I still have to add the fact that the derivative of y squared with respect to x is 2y, so 2y dy dx. The derivative of 4 is nothing, and the derivative of 0, which I forgot to write out, is also nothing. So let's subtract 2xy, and that gets me dy dx x squared plus 2y dy dx equals negative 2xy. Now let's factor out a dy dx, like that. That leaves me with x squared plus 2y equals negative 2xy. Divide both sides by x squared plus 2y. Divide both sides by x squared plus 2y. And dy dx will equal negative 2xy over x squared plus 2y. Now I have to plug in x equals 2. Oh, poop. I don't know what y is. Oh, but you know what I can do? In order to find y, I could just plug 2 into every x here and solve for y. All right, so instead of x squared, I have 2 squared y plus y squared plus 4 equals 0. So 4y plus y squared plus 4 equals 0. Let me rewrite that out. Y squared plus 4y plus 4 equals 0. Factor that out. Y plus 2 squared equals 0. According to the zero product property, y is going to equal negative 2. So my x is regular 2. My y is negative 2. Now we can plug stuff in. Negative 2 times x, which is 2, times y, which is negative 2, all over x squared, which is going to be 2 squared, plus 2 times negative 2. Wait a minute. You're negative 8. You're going to be 4 minus 4. Oh, actually, you're positive 8. Not that it matters, because that's undefined. My answer doesn't exist. All that.